So good morning. Yes, my name's Ross Newman. I'm a field applications engineer based in the UK. My job is to support customers in the military and avionics industries, as well as some customers in the automotive space throughout Europe and the Middle East and South Africa. So I work on the non-US side of the pond. My colleagues also work in the US. So Abaco Systems, I'm just going to tell you a little bit about what we do, what our value is, and then we're going to talk a little bit about open standards in military vehicles, and we're going to focus in on how GPUs can be used to exploit those open architectures. So Abaco Systems, we've been around for about 30 years. We're a new name because we used to be a small subdivision of the General Electric company in their embedded space. We focus specifically on very hardened environments, so very harsh industrial oil and gas. Our main market is military and avionics, so we design products to meet very harsh environments. We're located in a few locations. I'm based in the UK, where we do a lot of our manufacture. In Edinburgh, we have an Ethernet switch company where we do a managed switch software. We have a DSP company in Alphen in the Netherlands, and also over in Austin, Texas. We have an avionics business in Goleta. We have a high-performance embedded computer software center near MIT in Boston. And we also have a manufacturing facility in Huntsville, Alabama. So our value really is taking commercial technologies and hardening them for rugged environment. And that involves building boards to open standards. So these are commercial, off-the-shelf offerings that customers can take and build systems with very low or almost no NRE. We qualify our designs. We do advanced thermal management. So we do heat pipes in our thermal solutions, conduction cooling, air cooling. So we do all sorts of cooling technologies as required in different applications. We also do box level products. So we do boards. So there's some examples of some of the boards that we do. And again, the key to being successful in the COTS business is designing to open hardware standards. Okay, so let's get into it. We've only got 20 minutes, so we're going to talk about how to deploy a GPU into military applications. So I'm going to use the example of a tracked vehicle here. So you can see in a connected architecture, in a modern Vetronics vehicle, we're going to have all sorts of technologies. We're going to have sighting systems in the turret. We're going to have mission briefings, moving map displays, commanders displays, gunner displays, situational awareness. There are going to be cameras that need to be fused for 360-degree visions on this system. There are going to be connected vehicles that need to communicate, so there's going to be a secure gateway, radio frequency gateways. Again, there are lots of subsystems on this vehicle, and again, they're all connected via Ethernet over a very high-speed fiber backbone. So I'm going to focus in on the standard that I'm most familiar with in the UK, which is called the generic vehicle architecture, but also highlight some of the regional differences. In the US, they have a standard called Victory, which is being deployed in avionics and in ground vehicles. So we'll talk a little bit about the differences in approach against the US, the UK, and throughout NATO. So there's a lot of commonality, and some standards are being adopted across the pond. But it's also important to be aware of what those differences are, because the way that we would deploy a product will change based on the standards and the protocols that are used in each region. So we're just going to cover a little bit more and dig into one or two of these standards. So if we take a closer look at the generic vehicle architecture, this is a UK MOD standard. And when we talk about generic architectures, we're really talking about scalability. So the generic vehicle architecture is an architecture that can be deployed on a quad bike or a Land Rover or a tracked vehicle or a main battle tank. So it's an architecture that can be scaled to meet the needs of the vehicle. So it's really about scalability and open standards so that you can reuse the same processor on the quad bike that you can use on the tank. So you can move a box between vehicles and you have a very low risk, low cost solution that's portable and can be migrated between different vehicles. So I'm going to focus in just on the vehicle standard. It's important to understand the context. In the UK, they have something called the Land Open Systems Architectures, which is a collection of architectures. So the generic vehicle architecture is just one of 3 architectures that are defined under the standard, under the LOSA standard. So we have the vehicle architecture, which is, as we described, is for mobile platforms. We also have the generic base architecture, which is for bases, overseas bases. So how does the vehicle communicate with the base? How does the infrastructure on the base communicate? How do you protect your security and your borders? And then we also have the generic soldier architecture. So it's just the diagram there, just so you can understand that generic vehicle architecture is part of a broader suite of open standards. So we have the GVA standard. That also mandates another standard called DEFSTAN 2309, which is the Vectronics infrastructure for video over Ethernet. Now, having video on Ethernet is great for GPUs because every GPU technology that I've ever seen always has an Ethernet interface, so it's a low-risk way of inserting a new technology into an existing infrastructure. So we're going to focus in on the protocols that run over that Ethernet infrastructure. And that's true for all of the ground vehicles that I'm currently aware of. So that's great news for us, and we'll dig into that a little bit in a moment. So here are some of the roles where we can utilize GPUs into military computers. Here's an example of a box that we produce specifically designed for ground vehicles. You can see they have a special connector technology on the front called 38999. This is a gasketed connector, very rugged, very hardened, and all of the I/O comes out through these connectors. So these boxes typically contain a processor and a GPU. They can be hooked up to displays. And again, they can serve various functions. So the driver's display can be driven by one of these computers. The driver is driving the vehicle. He requires very low latency video. He's driving from the video streams, from the camera streams. He doesn't want to be sticking his head outside of the vehicle. So he has to have a very, very low latency stream from which to drive the vehicle from. In the back of the vehicle, you're going to have a commander. He's going to be looking at the mission objectives. He's going to be looking at the situational awareness. He's going to be communicating with the gunner and the driver. So in the turret, we've got the gunner. The gunner needs to calculate ballistics information. He needs to stabilize the gun. There's all sorts of uses for GPUs in the turret as well. So in the base of the vehicle, something that we did recently where we produced a video recorder, a rugged, hardened video recorder for capturing telemetry information, for capturing video information. So in the back of the vehicle, all of this situational awareness video footage can be captured on a video recorder, and if an event occurs and the commander needs to look at something that happened 5 minutes ago or an hour ago, he can call up that video stream and he can review the camera footage. So there's a lot of technology going into these digital architectures. Here's an example of one such architecture. This is a full GVA compliant vehicle. It's one of the first fully digital architectures that complies to the GVA standard. Abaco Systems are a major provider of both NVIDIA technology as well as Intel technology in this vehicle. It's one of the first vehicles to really leverage the GPU technology. So in this vehicle, in the turret, they utilize GPUs for the gunner. So the gunner is having increased autonomy for moving and manipulating and firing the gun, as well as in the base of the vehicle where we have the video recorder capturing all of the telemetry information and playing that back on demand to the commander. So this is a great example of a GVA architecture. The backbone on this architecture is dual redundant fiber optics, so it's a very high-speed backbone. And then off of that backbone, there are various switches around the vehicle onto which you can plug in gigabit copper Ethernet ports. So the reason that we have fiber around the vehicle in a ring is because it's not susceptible to noise, it's very high bandwidth, it's lightweight. The benefits of Ethernet mean that you have reduced wiring, you've got the benefits of multicast. So let's focus in a little bit more on how we can exploit this infrastructure. How can we exploit the deployed technology? So we have an Ethernet backplane. There's a whole plethora of digital video standards, but you will find that almost exclusively within military markets and also in some drone applications that we're exploiting Ethernet. Ethernet is a common backbone on all of these vehicles. All of the communications, all of the recorded footage, all of the audio goes onto that Ethernet backplane. The benefits of Ethernet are that you can go for quite long distances, up to 90 meters, but also you can have multiple subscribers. So we have the multicast capability, which is very, very important when you need multiple subscribers to a video stream. So we don't see the traditional automotive, single point-to-point connectors like 3G, HDSDI, or GSML. It's all Ethernet, which is great news for us when we're building our solutions and we just want to insert a capability into one of these vehicles. So here we have a reference architecture. So under the GBA specification for Ethernet, it allows for 3 types of video streaming. The first video streaming is a real-time protocol for YUV encoded video. So this is very high bandwidth, but very low latency. The benefit of streaming video scanline for scanline is that your camera can be capturing the first scanline of video. That scanline can then go out onto the Ethernet network and can be being displayed on the driver's display before the entire frame is captured. So each scanline can be transmitted and can be put out onto the Ethernet network before the first frame is captured. So you have this very highly synchronized display, camera and driver's display. So the driver's display can be, he can be viewing those video streams in as close to real time as is possible. So that's the benefit of the raw part of the standard. There's also allowed for JPEG 2000. Again, you can, it allows you to stream JPEG 2000. Not many people are doing this because you lose the benefits of the real-time nature, but there's some compression benefits. And then the third part of the standard allows for streaming RTP H.264 for compression. This becomes very important when you have a radio gateway, so I show H.264 down there, where you have a limited bandwidth RF communications network onto which you need to stream some sort of near to real-time video. So you may have, you know, maybe 300 milliseconds delay over that radio link, but again, there's no other way of streaming raw video. But on the backbone, around the vehicle, all of the displays are consuming uncompressed video. So that's important to understand when we look at the... oh, here we go. So in comparison, if we look at the US standard, we have GigiVision. GigiVision is prevalent in the US. The reason that GigiVision hasn't been adopted on this side of the Atlantic is it is a proprietary standard. It's a licensable standard. Whereas if we go back to RTP, RTP is an open RFC. Anybody can implement it. There's a lot of support for that in Linux. So in the UK, they tend to select open protocols and open standards. RTP doesn't work on its own when you're talking to appliances, so it's also paired with Distributed Data Service, or SNMP in the UK standard. In the US standard, GigiVision has a streaming channel and it has a control channel built into the same protocol, so you don't need DDS to configure and set up your cameras. It's all built into the GigiVision, so in some respects it's a little bit simpler than the UK version of the standard. But again, GigiVision is very high bandwidth, very low latency. Again, it's just a regional difference that you'll see when you start looking at ground vehicles. So I have this slide. When I do a longer version of this, we go into a little bit more detail. But really, the takeaway from this slide is when you're streaming raw video, it's very high bandwidth. So it's very important to understand the decisions that you make with regard to color space conversion. For example, here we're showing Bayer encoding, which is typically used in GigiVision. Bayer encoding, you can look at this if you want to Google it afterwards, but basically Bayer encoding allows you to encode 1 pixel for 8 bits of data. So each pixel consumes on an average of 8 bits per pixel. In the UK standard, it's a YUV encoding. It's a little bit more efficient than RGB, but you're up at 16 bits per pixel. Now that's important because if we look at the bandwidth that's required to transmit video streams within the vehicle, Bayer is twice as efficient as YUV. So we've got some examples here, a 640 by 480 stream with Bayer encoding at 30 frames per second. It's only 9 megabytes, per stream, so you can get multiple streams of Bayer encoded video. If you go and double that resolution and you do YUV encoding, you're up at 18 megabytes. And again, the problem gets gradually worse as you up the resolution. So if you jump up to full HD at 30 frames, you're up at 60 megabytes per second. So you're only really going to get one stream on a gigabit copper interface. Very quickly when you jump to 4K, and now you can't do it at all. You need to, you suddenly need to deploy a 10 gigabit interface to be able to stream that in real time. So that's why it's important to understand the requirements for real-time video in ground vehicles, and the bandwidth is something that you need to consider if you're going to tap into those streams. But again, the reason that is high bandwidth is is for the low latency. You know, there's no compression artifacts. The driver's not going to get confused. It's raw sensor information that they're driving the vehicle from. So now that we have access to those video streams, we can start doing some sophisticated computer vision algorithms, and we can start detecting things in those video streams. So we have the standard autonomous things that we do in automotive, image recognition, image localization. Again, that could be very important. If you want to distinguish pedestrians, and you maybe have a boy with a stick on one side of the vehicle and a man with a gun on the other side of the vehicle, then you might want to alert the commander that you might want to take a look out of the back of the vehicle, and you might want to alert the commander to the fact that somebody's been detected with a gun. So again, you can see there's a very immediate benefit there of being able to classify things in those 360-degree video streams. Segmentation could be very important for looking for obstacles on the ground. I have a customer talking to me at the moment who is very interested in trying to detect ground disturbance for obvious reasons, and segmentation may be useful there. We've already talked about localization. Another thing that all tracked vehicles have they have multispectral cameras, infrared cameras, and visible light cameras. So be able to fuse cameras together. Here you can see there's a smoke grenade, and you can see through the smoke if you fuse the infrared camera with the visible light camera. So that's a common thing that people like to do in ground vehicles. Stabilization, so for even for avionics platforms or for ground vehicles, stabilization is very important. Being able to track things, so if you have a mechanical gun, servo-operated gun, you can automatically track a target. So that's, again, something that we can use GPGPUs for, as well as generating ballistics information and firing options using GPGPUs. A lot of the cameras that you'll find in ground vehicles do not have ISPs in, so you get distortion in those cameras. So you can correct distortion with GPUs, so you can do basic barrel distortion and correction in the GPU, so that the information that you're seeing on the screen is more accurately reflected. And again, situational awareness, very basic stuff, but in vehicles, you know, the cameras are there, but you'll be surprised that they don't actually fuse those cameras together. They actually have to press a button and look at each of the 6 cameras individually. Being able to fuse those into a warped screen, or be able to put in that information into a headset, again, are things that people are looking at doing with that existing information. So those are the types of applications. So what kind of products can we put into those applications? So it's a very hardened environment that we're operating in. So the products that we develop at Abaco Systems are designed to meet those rugged requirements. So all of our products are designed for very high bandwidth on the backplane. They are designed for very low temperature. All of our products operate at -40 up to +80. So you can imagine a tank is left in a desert and it needs to start, or in a frozen environment, it needs to start first time every time. So we do temperature cycling on all of our products. We have an example of an embedded module over there. That's actually a Tegra K1. And then we have discrete graphics, 3U VPX. We have Maxwell and moving to Pascal in this 3U VPX form factor. And then we have hybrid solutions for radar customers. So a lot of GPUs are used for ground-based radars. We have a lot of customers who want to do DSP on GPUs. And we have the 6U product on the right here, which has Intel and NVIDIA chips. And in the middle there, you can see a big PLX switch with a PCIe Gen 3 connecting the two together on a single PCB. Again, this is very popular with radar customers. It also has an XMC mezzanine site, so you can do A to D conversion. You can capture all of your information from your antennas. So again, very useful for our DSP customers. In ground vehicles, we have products that are specifically targeted to that application. We have the Jetson TX2 module now packaged up in a product that we call the GVC 1000. So that's a Tegra TX2. It has a dual 10 gigabit Ethernet interface on that carrier board. So on the PCI Express, we have dual 10 gigabit Ethernet plus the single gigabit Ethernet interface that comes directly off the module. So on the carrier card, we've implemented an Intel NIC device for 10 gig. We also have a large SATA device on there, so 128 gig of additional SATA. That's on top of the 32 gig on the module. We also have Milcan. Milcan is a derivative of the CAN bus technology, which brings determinism into military applications. So it's a modified version of the CAN interface used in military ground vehicles that guarantees delivery. And then at the top end, we have the GVC 2000, which is desktop performance. It's discrete graphics, Maxwell processors, 1024 cores, paired with the Intel Xeon processor, 16 cores. So this is a no-compromise number crunching machine with a desktop performance. The small box is around 30 watts. This big box is around 100 watts. Abaco Systems also do DSP libraries and technology that can be used to accelerate your algorithms on AVX and on GPGPU. So we have a portable set of software libraries. So we also provide a little bit of middleware. We have an image processing library to enable you to do situational awareness, video stitching. We have all of these algorithms available to our customers. And again, these libraries are now being extended to include automotive as well. So being able to put in sensor fusion, LiDAR, radar information, and to be able to augment that information and display that to the customer. So today, we're taking both our hardware and software technologies to automotive customers and saying, look, if you need this kind of technology, we can put this into a custom package and put it into the boot of a car. We're already doing long life cycles. We're already addressing obsolescence and extended life. We think that's a great ability that we have in the military space. And if we look at a cost reduction and custom form factor, we can provide that technology into automotive as well. So that's my presentation. If you have any questions, then, yep, I'm going to be around. And thank you very much.
Thank you, Ross. So any question? Sure there are questions, no? Time for lunch? So.
I am interested in how many parallel video streams you're able to route in the tank. So are you able to look onto all 360 directions simultaneously?
That's a common requirement. I can't give any specifics for any specific platform because it's classified, but generally a commander can switch. So the minimum is a 4x4. If you see any traditional military display, it's usually a 4x4. There may be 6 or 8 cameras on some vehicles, but the buttons are actually defined. The man-machine interface is defined, and there is one display mode which gives you a maximum of 4 at any time. Yeah. So at any one time, the current situation is at any one time you can view 4 simultaneous streams.
So it requires actually more than one Ethernet cable capable of only 1,000 megabits.
You'd be surprised at how low resolution these streams are in
really?
Current technologies. We're talking about 640 by 480. So gigabit Ethernet is sufficient for current video streaming. It's not HD. You know, this is the future for ground vehicles. Ground vehicles is lagging way behind what we're doing on drones and in other platforms. So there is a question of how do they move to these higher fidelity cameras. Then they need higher fidelity displays. It's a big problem in military. But at the moment, it's not untypical to see video streams at 640, 480, maximum of 1,000 by 1,000.
Okay, thank you.
Anyone else? Oh.
So apart from those computer vision libraries that you have, the deep learning applications that are built on top of that, do you also provide them, or is that built by your customers?
No, so we're really in the business to build the platforms, and we have a little bit of enabling technology middleware to get our customers started, but we don't provide complete solutions. So we are open architectures, we're software agnostic. Some people run Windows on our platform, some people run VxWorks, some people run Linux. Again, we don't kind of dictate where the application needs to be or where it needs to go.